my interest is related how to understand congestion and control congestion in large-scale networks. And clearly what we can say that traffic networks are complex networks because you have different modes of transport competing for limited space. And what you also have, you have these components that are adapting as they're involving humans, that they make decisions how to change route, how to change mode. And then you have the operators of the system that try to improve the system, but having different objectives. So public transport operators try to improve public transportation. Uber operators try to maximize their profit. So many of these decisions are usually conflicting. And even if we claim we're in the era of big data, we also have strong limits in the predictability of the system, making these competing operators to cooperate. And also the complexity limits the centralization of decisions. So that's the reason transportation is an interesting field. And if this looks complex to you, this is a drone experiment we did a few years ago with all the trajectories being publicly available. Here you see only 5 of them monitoring traffic. What we saw before was in the corner. And if you want something more complex, we also did an experiment last year again with drones in Nairobi in Kenya, where you can also see complex interactions. Here you see motorcycles and pedestrians moving around a very congested roundabout and so on and so forth. So here is an example of looking at real data highlighting these complex interactions. So what you see in the top, you see trajectories of cars and trajectories of motorcycles, and clearly you see a very different maneuvering behavior that actually has inspired many researchers developing detailed models of how vehicles follow each other, how they change lanes, and so on and so forth. My talk will not focus on that, but it will focus on how we can understand and control large-scale networks. And given this complexity, I will try to come up with a conceptual approach that, of course, has a lot of technical details that can give answers possibly to different transportation systems. And I have 2 examples to showcase that. So let's start with some basics. So I think it's almost 100 years ago, the concept of the fundamental diagram between road density and road flux. So if we take one point on the road and we measure density and flow, what you get something on the left that it has a unimodal shape, but also a lot of noise. If we look spatially and we aggregate, let's say these are data from the city center of Geneva, the network density versus the network flux, the scatter disappears, but also hypercongestion disappears. So we don't see the decreasing part that highlights high congested conditions. So what we should look for a compromise somewhere in between, that we can cluster a network in regions that have well-defined, we call it macroscopic fundamental diagrams, with a congested part, but at the same time, we're able to have less scatter. And we have one joint paper with Dirk back in 2010, where actually we identified some conditions for which these clusters should behave well, and this is related with the spatial distribution of congestion. But this is out of discussion for now. Okay, so here what you see some taxi data from a mega city in China. And what we looked at in the 6 largest components of congestion. So we try to highlight, to give a flag to a link if it is congested or not. And yellow is the background. The different colors are the 6 largest components. And you see the evolution over time. So interestingly, you see that in the middle of the peak hour, you have a gigantic component that actually goes almost all over the network. And I think Shlomo has also seen similar patterns in other data sets. So what is interesting here, if I try to estimate network density versus network flow in all these different clusters, and each point represents different time, and each color is a different cluster, what we see that even if the penetration rate of taxi is very little, less than 1%, you get well-defined relationships with a clear tipping point. So possibly if we can observe this phenomena, our objective would be that we try to keep the number of vehicles in the network at this point that will maximize the flow. Conceptually, this is the concept. So how we can do this? I talk a little bit about clustering without a lot of technical details. So we developed a snake algorithm that the idea is you start from a road and you grow like a spanning tree in a way that your tree attracts links that are as similar as possible to your existing links. And what you see here, you see the size of the tree, and you see the average speed and the standard deviation of speed. So interestingly, what we see is that as we grow up to a value of 100 links, our standard deviation is small, which means we create a cluster with similar speed. And if we continue to grow, you see that we start having dissimilarity. So the idea of this algorithm is that if we run snakes from many different parts of the network, and we try to create similarity matrix between different links, we can apply classical techniques like negative matrix factorization and divide the city in homogeneous clusters. And here is an example that we see of applying this approach in the real data of Shenzhen. But what we know is that congestion is not a static process and it changes over time. So similar concept can be applied for dynamic clustering. But what is important to remember is that transportation networks have strong spatial correlations. So if you have congestion in a part of a city now, after 5 minutes, you expect that this cluster is not completely changing, but either it grows or it shrinks. So these spatial correlations can help us to solve this problem efficiently and with results that make sense. Okay, so now I start to introduce the concept of traffic management. And let's start from the basics. So let's assume that we have a very simple network with only one region. And in this network, you have two types of flows. So you have internal flows that you are not able to control. So you start the engine of the car anytime you like and you move around. And you have flows that are coming from outside. And what you have a perimeter here with traffic lights. And these blue arrows can be controlled by giving more green or more red. Okay? So if we assume that this region has a well-defined macroscopic fundamental diagram between number of vehicles and outflow, this is a very easy dynamic system, and the optimal strategy is a bank-bank control. So if you are above the critical value, you restrict as much as you can. If you are below the critical value, you let as many vehicles as they want to enter the city center. Okay. But what we know is that transportation networks are heterogeneous. And after clustering, you can divide it in different regions. And you have more control authority. You have more ability to control the network. So what you can control the intertransfers between different regions. And somebody might say, okay, but this is an equally easy problem. Because if I can keep all my regions at the critical value that maximizes flow, this will be optimal for everyone. Yes, but indeed this is not always feasible because what you have antagonistic behavior. So if I try to protect a region of a city by not allowing many cars to come, this means that these cars should be somewhere else. So there is competition between the different regions. I cannot keep all the regions of the city at the maximum. Somebody has to pay for congestion, right? So we spent a lot of effort, actually, in the last 10 years to develop different type of control algorithms to control these networks. And I would like to give some intuition how we can implement this in general in large-scale networks. So the idea of hierarchical control is, this is an example of model predictive control. I think it can be skipped. This is just a method to control dynamic systems. Okay. So the idea that I will present here is we have a two-layer control where at the upper layer, we divide the city in different regions and we choose only some traffic lights in these boundaries and we try to control the intertransfers with an objective, let's say, to minimize total delays. Okay. At the lower level, we zoom in and then we apply local controllers at specific intersections with an objective to improve conditions locally. And actually, we try to investigate in this paper how these two layers can cooperate well and what is the added value of this hierarchical control versus applying only upper or only lower. Okay. And at the lower level, we don't apply our algorithm, we apply a quite established algorithm developed by Professor Varaya, which is called max pressure. And the idea is simple. So if you have many directions at an intersection, each direction is pushing and is pushing with the strength, which is the Q length. And the more you push, the more green you get. Okay. But this is a local strategy because you only push with the Q length that you have in this specific intersection. Okay. So we don't need to look at the equations, but this highlight what is the pressure, why you have two terms, because on the one side you push, but on the other side you need to have enough space downstream for these Qs to be able to move. Okay, so if you don't have enough space, your pressure will go down. Okay. So you sum all the pressures and then you distribute the green time proportionally to the pressure from each direction, let's say. And a question we had is, should we apply max pressure everywhere in all intersections? Somebody might say, yeah, if you have the data, why not? But still nowadays, data have a cost because you need to install sensors to measure all this flow. So if we can apply this by using a subset of intersections, why not? Okay. So the concept we introduced there is how we choose some critical links to apply the max pressure. Our idea is that we choose links that they have a lot of Qs. We choose links that these Qs vary over time. And we also choose links that this congestion has long duration. Okay. So we apply a simple machine learning approach to choose these links. And then we look at the results of this two-layer control. And we test it with medium demand and very high demand. Okay. So what you see in the horizontal axis is in the percentage of links we put the max pressure. What you see in the vertical axis is the improvement we get compared to fixed time control. Okay. So an interesting observation is that if we choose in a smart way where we apply the max pressure, we do better if we apply in a subset of links than applying everywhere. So you see that with 25%, we do significantly better compared to apply everywhere. So initially we got surprised by this result, but if you consider that the difference between local decisions and decisions at the global network, you can understand why this happens. Simply speaking, max pressure tries to send vehicles in the city center, and once you reach the city center, you are stuck. So going fast in the beginning is not ideal. I remember in one of your first papers, Dirk, you were having this slower is faster effect, which I believe, even if this is in a different setting, the concept is similar. Interestingly, if we have very high demand, and we had this discussion over the break with Stefan that I would say he also developed probably before max pressure and another algorithm of similar type, you see that the improvement you get only with lower level controller is not significant. So now let's go to add the two layers, both the upper and the lower layer. So for medium demand, it's interesting to see that what we get when we apply both is very similar to max pressure only. So somehow, when the network is not extremely congested, spatial interactions are lower, and by only looking locally, it's sufficient. But if you have high demand, a combination of both perimeter control and a lower level controller is very beneficial for the system. So you see that we reach improvement 15%, while before it was close to 0. Okay. So interestingly, if we look at the network fundamental diagrams with the different strategies, this is very interesting. So max pressure has the best macroscopic fundamental diagram, the highest possible network flow. So somebody might say, look, this is very beneficial. I apply this strategy, I get the maximum possible flow. This is the best for my system. Unfortunately, no, because this flow, you send it in areas that have a lot of attractions of trips, and you end up being congested very soon, and your flow will go down. So that's the reason that local strategies are not always beneficial. So we have about 7-8 minutes. It's enough. Okay, good. So let's change completely topic, but I believe the concept will remain the same. So let's look at a completely different problem, which is we have on-demand transportation like Uber-type vehicles. And the idea is that if we have a central operator, maybe we can rebalance empty vehicles in different parts of the city with the objective actually to offer better quality of service. So this is the problem we're looking at. Again, this is a complex problem because you have thousands of these vehicles and you cannot optimize the system in classical ways, let's say by solving a dial and write problem for 2,000 vehicles. It will be very difficult. So I think I already defined the problem. When you have high demand, maybe you don't have enough taxis, or you have very low demand and many available taxis. So this is what we want to offer. These pictures were created by ChatGPT by my students. I don't know how to create, but it's very interesting. They look nice when I saw them. Okay, so we got the Shenzhen taxi data and we created our own simulation. And what we checked over here, the fleet size, the willingness of people to share. What means willingness to share? It means that if two people are positive to travel together and you can identify a trip as an operator that for both of them, the detour is less than 20%, they match. If they're willing to travel, but the detour is very large, they will not match. Okay? So then we investigate the performance of the networks for different types of these, let's say, control strategies. So here, what you see, the average waiting time of users as a function of the fleet size. And A and B, what is the difference? If parking strategy is deactivated, empty vehicles will go around all the time. If parking strategy is activated, empty vehicles will go to some depots and then they will be sent back to the system when required. So interestingly, what we see here is that the average waiting time decreases with the fleet size. But if you have a lot of fleet, you will have extra congestion, so your waiting time will go higher. So you're close to somebody, but because you have a lot of congestion, it takes more time to reach him or her. Okay. Waiting time is only one part of the trip. So let's look at the total trip time. What we see that the total trip time is minimized for smaller fleet sizes. But companies like Uber want to attract more passengers by minimizing their waiting times because they compete with public transportation. So somehow, if we care for the system optimum, it should happen with smaller fleet sizes than what these companies care to attract more users. And if we approximately estimate their revenue is maximized also for much higher fleet sizes. So this is something to keep in mind, that if we don't intervene in the system with some regulations, incentives, etc., maybe we will end in monopolies where these companies will make a lot of profit, but we will suffer as transportation travelers. Okay, and I will finish by making an analogy of the perimeter control problem with the vehicle rebalancing. So what we do here, we have a city, we divide it in different regions, and we try to see how many empty vehicles we need to move from one region to another with an objective to serve as many customers as possible. While at the lower level, we try to redistribute the empty vehicles in a way that they cover more area. So it's like a coverage problem, which is quite well established in robotics. So I think I will not have a lot of time to go into technical details. But the upper layer is actually a classical control problem that we can solve with model predictive control, or we also tried data-driven methods like DeepC that was developed by the group of John Ligeros here at ETH. And if we go to see some results, actually you see interestingly that the dynamic equations here have a similar concept with the previous problem are flow conservation equations. And this is the lower level, the coverage. So each taxi can cover an area around it, which is, let's say, is maximum waiting time of 5-10 minutes. And you have some demand profile, and you have some initial distribution, and actually with some type of distributed control, taxis are pushing each other to be able to meet the expected demand. I think this can be skipped. So we apply this in the taxi data of Shenzhen with the real demand we had from the taxis a few years ago. And interestingly, we look at the performance of the full framework versus upper only and lower only. And here we have two performance measures, which is the average waiting time and the abandonment rate. Abandonment rate is that we're not able to reach people within the 10 minutes, so they quit the system and they travel in different way. So interestingly, the full framework is doing significantly better than the two levels independently. And actually, if we don't do control, what we see is that even if our fleet size is doubled, if we don't do an action, is much worse compared to the smart framework of rebalancing. So what we try to say here, the takeaway is that if we're able to integrate smart operational strategies, actually we can serve more users with less fleet size, which can be beneficial for the network because you have more space available. So I think I can finish here. What we see here, you see the evolution of the time of the types of vehicles. So you see a lot of idle vehicles in the no control, but in bad locations, while actually we can have a better distribution of the vehicles with our rebalancing strategies. So here you see just a simulation of how vehicles are moving around. So I think I am done, and I'm happy to answer any questions.
All right, thank you so much, Nick.